you very much for that kind introduction. I wanted to say I'm very pleased to be here today and really appreciate everyone's time coming to learn about this and giving me the opportunity to share with you all. All right. So I'll start a little bit by telling you about myself and the Concord Consortium, and then we'll dive into the tools that we're going to be looking at today. So I'm a former teacher. I taught chemistry actually for 14 years as a high school chemistry teacher. And my work in the classroom is what inspired me to start building these tools. I also have a background in computer science. And when I started teaching, there weren't very many tools to help with teaching STEM. And I found myself as a chemistry teacher, imagining this world of unseen atoms and molecules, and I'm waving my hands all around, trying to get students to get the picture that's in my head. And I realized that what I really need to do is provide them opportunities to be able to explore this unseen world. And so some of the first work I did was on building molecular dynamic simulations, or simulations of atoms and molecules. And that has led me to where I am now. Two of the tools that we're going to learn about today, SageModeler is a simulation tool. So it's sort of extending that early work, but in this case, the students are building simulations. And CODAP is a tool for doing data exploration. The thread that is common through my work is I want to support students in being able to learn science, technology, education, math by doing those fields, by engaging in the practices, by really discovering the concepts and the fundamental principles for themselves. And so we're going to learn about a couple of tools today that I think will help us with that. The Concord Consortium that I've been working with for the past 25 years is a nonprofit institution whose goal is to do research and development around how technology can best be used in education. And this vision has really made leaps and bounds over the past 25 years. And I've been really happy to be proud of that. And I'm excited to share a couple of tools that we have today. So you'll see on this first slide here, there's a link that will get you a link to these slides. So if you want to follow along or click on any of the links that I'm showing you, then you're welcome to do that. I will say that with the short time we have today, we're going to be doing an introduction to the tools. You won't necessarily be an expert in using them by the end of this webinar, but we hope to, as mentioned earlier, we hope to have a series of webinars to build people's skills and confidence in these over time. All right, so we're going to start talking about CODAP. CODAP stands for the Common Online Data Analysis Platform. And it's an immersive data environment designed for students. We've had students as early as actually grades 3 and 4 use CODAP, but primarily grades 5 through 14 are undergraduate. It's free, it's open source, it runs in any browser, and designed for students. So while you may get excited to use this as a data analysis tool in your own work, you're welcome to do that. The main goal for this is really to help students learn how to engage with data, how to explore data sets, how to make their own sense of data. This is CODAP's based on research starting in the early 1990s and continuing through the present. Bill Finzer is the lead on developing this particular tool, and it builds off of work that he had done back into the 1990s in building statistics tools for the classroom. And he joined Concord, and he asked me to join him in helping to co-develop CODAP. We've been working together for the last 10 years or so. CODAP is growing by leaps and bounds. We had over 1 million active users last year. That's translated into 18 languages. And if there's anyone out there who would like to help translate it into new languages, we're always open for that. And it's used around the world. It's been growing exponentially for the last 10 years. So, and with no sign of slowing down so far. So we anticipate this tool to continue to grow and be available. One of the things, and you'll see in a demonstration shortly, that makes it so popular is that the way you interact with the data doesn't disrupt your ability to be thinking about questions and asking questions. You don't get bogged down in the technical aspects and graph wizards with 10 different settings in order to just make it one visualization. You'll see that we can quickly make graphs and other visualizations, and that there's some special features about how they're all linked together, which you'll see. Another component is that CODAP is extensible, so that pretty much anyone who can do some coding can write their own little app that will run inside CODAP and extend its features. And we see this as actually working across curricula, not just in math and STEM fields, but we've been using this in English classrooms and history classrooms. And so we think that this is a tool that really has broad application. All right. You'll see here the main link to our website about CODAP is over here, codap.concord.org. And I get to introduce to you today our new version, which is not officially out yet, but we're going to do all of our work today in the new version. Hopefully we won't run into any bugs, but this V3 version 3 beta version is the link that we're going to be using. And we hope that in a few months, the current release will be the same as that beta release. But if you want to use something in the classroom now, you're going to want to use this current release link. But for today, we're going to be looking at this, the beta version, which is our new version. All right, so I'm going to start by demonstrating some of the core features, and I'm going to launch a data set here that is of elephant seals that were tagged, and data was collected from them over the course of a year. So I'm going to click on that to launch it. Notice I can set up a document that's ready to go for a classroom, and we'll talk about how to do that a little bit later. And let's take a look at our data set here. You can see that we have, there's an animal ID, there's the day of measurement, the date of measurement, the month of the measurement. We have positions with longitude, latitude, how far they went, how fast they went, how deep they swam. And then we have some satellite measurements to correlate with temperature of the water and chlorophyll. And then there's a curviness measure as well. So this looks like a regular spreadsheet. But I'll tell you that this table is a bit different from other tables. For example, we see animal ID over here, and there are 858 rows. And if I scroll, you'll see that the ID eventually changes. So we have more than one animal. And one thing I can do in a CODAP table is I can create hierarchical structures or groupings. So I'm going to take animal ID and drag it over to the left. And now, if I click on animal 546, it shows me, highlights all of that animal's data. We've actually found that, in fact, this is much more intuitive in the way that students, and in fact, most normal people, will think about data. If I were to look at this data set and describe it to you, I would say, I've got 4 animals and I have a whole bunch of measurements for each animal. But the way that we think about with spreadsheets, the way it's done with spreadsheets is I have to enter animal ID like 365 times because spreadsheets don't have this ability to create these hierarchical structures. So in fact, this idea of having a hierarchically structured table it matches better with the way people think about data, the way they're conceptualizing the data structure. And so this helps with the analysis as well. All right, let's make a graph. So if I want to make a graph, I'm going to click on graph, and then you'll see that what it does is it basically just shows me all of the points that are going to be on my graph, but it's not configured yet. I haven't put any axes. And each one of these points represents one measurement. You can see if I click on one that it shows me where that measurement is in the table. Now let's say that I'm interested in depth. I wonder how deep they're swimming. I'm going to drag that onto the x-axis here. And notice already I've discovered an interesting pattern that they tend to dive down to a depth around 600, 650 meters, or tend to be swimming at a depth of 335 meters. And so that in itself is an interesting discovery. And notice how quickly I was able to make that graph. I just dragged the depth attribute from my table onto the axis, and there I've got it. So this we would call it's a dot plot, and so the more animals that are at a particular depth, that kind of stacks up. So it's like a histogram. It's a type of histogram. We can also, of course, do scatter plots. So let me do a graph and see if I can find a relationship between something like, I don't know, distance and speed. So I'm going to drop distance here and speed here. And they're very well correlated. In fact, that's so well correlated, I think they're using one to calculate the other. So, and that there's an interesting one sensor, I bet, that seems to be different than the others, or one animal. And one of the things you'll notice is within the graphs, there are various buttons over here to bring up palettes. And the measure palette is a pretty good one. Notice here, because this is a dot plot, I have certain kinds of things like mean, median, standard deviation, those types of things. And I can add those onto my graph, and I can explore those as well. This is a scatter plot. And so over here, I don't have those. I have things like a best fit line, or I can plot functions, or I can have my own movable line if I want to say, well, I'm curious about what is the slope of this particular one. Now let's try a few other things. In fact, I might get rid of this one. And I'm going to make I have also a map here, and because I have latitude and longitude, if I click on that map, it shows me a map of all the animals' tracks. If I want to know which track is which animal, I could drop animal ID into the middle of that. So now I have a graph that's showing me all the animal tracks, and I can even see which one it is. If I click in the legend, notice I highlight all the points related to animal 536 here, also highlighted in the table, and also highlighted in my graph over here. Turn off those measures so it's a little bit easier to see that. So we have what's called dynamically linked selection between all of our data representations. So I might be interested in, for example, let's look at a graph of speed like we did of depth. Okay, that's very interesting. I wonder if the speeds change by the month. So I could grab month and drag that over to another axis. Suddenly, I have a dot plot for every month. And if I wanted to add some measure like the mean, I could do that, and we'll add the mean to each of these dot plots. I notice here there's some interesting patterns that sometimes they're much slower and sometimes they're much faster. I wonder if that's related to the map at all. And in fact, I could explore this in a couple of different ways, but I'm going to use the selection in the map and say, it looks like they come out here and there's something interesting going on in this part of the ocean. So I'm going to select over that and notice what lights up. it's almost all August and September. So, and when they're moving the slowest. So they're moving quickly out to this spot, and then they're doing something around out in this area. So we're starting to discover things about the behavior of elephant seals. And if I look up some things about elephant seals, I may find out that they tend to go out to a certain spot, and that's where they have feeding grounds and breeding grounds. And so I'm starting to find evidence for some maybe conjectures I have about some claims I might be making about the way that they're behaving. I want to come back to the table, and I mentioned how the table is different from other tables. Now notice how we have this structured sort of by animal and then by measurement. But what if I wanted to calculate something like the average or mean speed of each animal? Well, this little plus here allows me to add a new attribute, and I'm going to call that the mean speed. So I've created a new attribute, and I could go over here and try and calculate all those things, but I can put formulas in to CODAP tables. And so I'm going to click on that and get edit formula. And you can explore all the functions here. There's various functions. This would be some kind of statistical function, and you can see how it's set up here. And then if you click on this, it will also give you, it'll insert it. Or if I click on the I over here, it will give you a whole set of instructions about how to use that particular tool. Now, once you become familiar with the kinds of functions, I usually use this type ahead feature. So I start typing mean, and I see, oh, there's the function for mean. And I want the mean of the speed. So there's the speed variable. So I can quickly create functions using that type ahead. And I apply it. And now I have a mean speed for each of my animals. And then in the same way that animal ID is draggable around, so are my formulas. So for example, if I was wondering what's the mean speed of all the animals, I could just drag this all the way over to the left. And now I have the mean speed of all the animals together. So you have these very flexible, calculable attributes. And you can just, depending on where you place this, it will calculate the mean of that group. All right, so this was my initial demonstration of CODAP. And again, we're just touching on some of CODAP's features. And I know I did a lot very quickly, but I think what you can see when we were looking at this over here is how easy it is to make graphs, how easy it is to wonder about something, and then try and make representations to try and help you answer the questions that you're wondering about. All right. Let's go back to this. Now, one of the things that I think CODAP is a great tool for is helping students with the claim evidence reasoning framework. Right, so many of you are familiar with this, but I'll just give a brief overview. So a claim is a concise statement that answers a question or a problem. I think something is true, or this is my answer to the question of what I think is the correct answer. Evidence is the data or observations that you make that can support the claim. So that could be structuring the data table in a certain way and calculating certain attributes. It might be creating certain visualizations. And then the reasoning comes when you link. So here's the visualization, here's how I'm interpreting it, and how I believe this supports my claim. And so CODAP is a great tool for coming up with all kinds of ways to generate evidence for claims and then to explain your reasoning. In fact, if we, let me Go back to this. And one of the things that you can also do here, notice we haven't looked at all of the tools up in the toolbar here. One of them is a text box. So you can actually set up documents that have questions in them and students can answer them, or you could just ask them to write a claim and describe their evidence and their reasoning and provide those all here. I'm zoomed in a bit, so I don't have a lot of desktop space here, but I want to make sure all of the text is visible to everyone. All right, so with that in mind, let's look at another example. Now, this is one that elephant seal data was something that I had before. But I want to show you that there is lots of data out there that you can bring in to CODAP that is localized to your area. So I did a search for something similar kind of data that is local to this area, and I found some migration data for the common kestrel. And so we're going to look at this data set in a minute, but let's think about what claims we might be able to make or want to make about this migration of this. It's a single bird. We could maybe talk about the timing. We could talk about where we think the kestrel stops or what kinds of flight patterns it has. And then we want to think about what evidence we could generate to support our claims, and then how we might reason through that. So I'm going to launch that particular document. So this is data local to this area. I see there's a latitude, longitude. Whenever I see there's location information, I typically want to put a map out there. And so, okay, well, we can see this pattern. Oops. And from what I can tell, it's hard to know exactly where the starting and stopping point is. It may be on the ends, but it might be somewhere else. We can look at the data, what kinds of attributes we have over here. We've got timestamps for all of the data. We have the latitude and longitude, which is the position. So if I click on one, I'll see the data for that. We have the ground speed, and we have the height that they're flying at. So I also have this other piece of information, which if we look in the about the data, and I can expand this by looking at this, it shows where I got the data from. And you can find descriptions of the various attributes at that point. This, I happen to know, will tell us about the data, something about the data. And when it says 0D, that tells me that there's missing data. And notice all these 0D ones. In fact, that might be one of the first things I want to address. So how might I do that? I'm going to drag this over to the left so I get unique values. And I have, let's see, 3D ones, which seems to be the majority. We have some 2D ones, and we have this 0D, which is just missing data. So I might leave this here, or I might talk to my students, what should we do about the missing data? We could remove it. We could hide it temporarily. And that's done over here in this data option. So in this view option. I can either set aside the things that I've selected or set aside all the things that aren't selected. I can also choose to delete the selected ones. And in this case, since they don't have any data in them, probably it might make sense to just delete. All right, now let's think about what I might want to do next. Well, I am curious about another feature that I haven't shown you, which is I can turn on what's called a grid on the map. And I can adjust the size of those grid points. And what they are, and I'm going to zoom in some parts of this. The darker the color, the more points there are in that part of the map. Now, one of the things that's interesting is it says that there's 286 cases here, but I wouldn't have seen that without this turning on this heat map, right? And if I zoom in, I'm double clicking here to zoom in, you can see we have a large cluster of cases all at this one point at the end. So that might tell me if I wanted to make a claim that this is one of the places, this is one of the ends of the migration routes. This is one of the places that they stay, because I see many, many measurements in this area. Now we might be interested in when those measurements are. So I could make a graph and add the timestamp here. And we can see where all, this is at least just a distribution of all the dates. And then I could highlight over this group. And we see basically it's from May to September. They're spending all that time in this one place. In fact, it looks like it's almost half the data points. So I find that fascinating itself. I thought when I first looked at this, I thought, oh, they're spending a lot of time migrating from one place to the next place. And here I'm going to zoom in again. And because I saw that dark red, there's a lot right here. So I'm going to click my select tool on the map and select over there. And that's the other part from January to March. I might be interested in the height of these. So I can add height to this graph. And now that's very interesting. I see that there's, I'm going to zoom back out on our map here so that as I select things here, we can see it in both places. And notice that there's basically two heights. Now, when I first looked at this data set, I thought, oh, they're flying high up here. And when I selected this, I thought, well, wait a minute. There's some points where these exist, but a lot of these points are in this area that we looked at before, where they're staying. And what I ended up doing is I ended up looking up this region, and that's the altitude of the land in that spot. So they actually are spending a bunch of time down on the ground, but it looks like they're flying high. And then if you do the same thing for this other set over here, you'll find that most of those points are at the other end, or we'll see a lot of them at the other end. And down here, even though this is near sea level. So it's interesting things that you can find out. You could bring in other information that you know. And notice we've now are able to make certain conjectures about where we think they are, why we think the data explains that they're in these two places, because this is the altitude of that location in China, and this is the altitude of the location in Thailand. And so you can see here, I've just come up with ideas, I've made connections, I've made various graphs, and this linkage between all of the representations, I think, is one of CODAP's superpowers, because it really makes it possible to explore things that you couldn't explore in any other way, or at least not easily. All right, so let's talk about how, if you wanted to use it, how would you use it with data that you care about, or that you've found, or that you've generated in your classroom? Because sometimes you're going to find data online and you're going to want to pull it in. Sometimes you might be doing a lab, an experiment, and you want to have that data in CODAP. Maybe you're conducting a survey, you want to pull that data into CODAP. So there's lots of options for doing this. So let's look at how we would do that. I'm going to click on this. I pulled together a quick Google sheet of global mean sea level over time. And so what I have here is it's dated from 1850 all the way to, when's our last one here? 2013. This data that I found online. And so there's a this is the sea level, global mean sea level. Um, this is the sort of the uncertainty around that number, and we have a lower bound and an upper bound. You might say, well, how did I get this into CODAP? Well, I want to show you multiple ways that this can be done. The first way is I'm going to download this as a comma separated values file, CSV. It's a common file format that you can find lots of data in, and any spreadsheet program can export into this. So if you have data in a spreadsheet, you can create a CSV file. So I'm going to click on that, and I can see that it downloaded. And I'm going to open a new CODAP. Let's see. Trying to get the beta version. You have links for, oops. All right, I guess I'm going to need to jump back and get my link to CODAP here. Here it is, CODAP beta. So we got a new document, and in my downloads, if I click on this to look at my downloads, you can see here's that CSV file. Now I could either drag it in from my file system, or I can just drag it in right from the downloads in the browser. So I drag it into CODAP, and there's my data. I can now start working with it. So what are some other ways that we could do that? All right, let's reload this like we've got a brand new CODAP. I could go back to my sea level rise document. I'm going to Command all, select all of the data. I'm going to copy it to my clipboard. I'm going to come back to this, and when I'm going to go to tables, and it says new from clipboard. So if I grab data from a table and put it into my clipboard, I get into CODAP. Now that could happen from a spreadsheet, that could happen from a web page, that could happen from any sort of table structured data. If you can highlight over it and it was structured as a table, its underlying structure, then we should be able to import it by copying and pasting in CODAP. And of course, you can move stuff from one CODAP document to another by clicking on here and either exporting it as a CSV or copying to your own clipboard and taking pieces and going from document to document. The other another option that I want to that I can't demonstrate for you in beta version. I could in standard CODAP, so maybe I should show you in standard CODAP. Yes, I will. Is this is the current production version. Notice a little less colorful, not as exciting, but this is coming soon to the beta version. I'm going to grab this URL and I'm going to drag it over here and hover over my CODAP document tab, so that comes forward, and then I'm going to drop it in there. And so I just dragged and dropped the URL from my Google Sheet, and there it is in CODAP. So multiple ways that you can pull data in from external sources. As I mentioned, that won't work on the beta version yet, but it does work on the production. All right. Now, one other thing that I wanted to mention is, of course, you can always type data in directly to CODAP, right? So manual entry is an option. And I want to do an interesting, fun kind of math example. So I'll show you another way of using CODAP. So I'm going to start with a empty, with a document that is, we're going to explore rectangles. If you want to think about how can I use CODAP to make a more exploratory math experience for my students, well, let's look at this. Now, you can see here I've set up the document which says, imagine you have a large collection of rectangles. What might be the relationship between area and perimeter? And it asks the student in this case, write the first conjecture you have that you think might be true. I'm going to go on to this next sort of slide of CODAP. I'll explain what this story builder is later. It's a plugin. Remember I mentioned plugins at the beginning? We'll have a little bit of time to explore plugins. And it says make some rectangles. Well, there's some ways I could do that. I am going to create a new table. And so I've made a new table and it has one attribute. And I'm going to rename that. And I'm going to call it length. Now I need a few other things if I want to play around with rectangles and their perimeters and their areas. So I'm going to make another width. I'm going to make another attribute here, and I'm going to call it perimeter. I'm going to make another attribute, and I'm going to call it area. Let me make my table a little bigger so we can see all those. So you can see here now I've made my own table, and I could, if I started double clicking in here, I could start typing in some random numbers for my lengths and widths. And I could even calculate those by creating a formula in perimeter. So let's go do that. I'm going to say it is 2 times the length plus 2 times the width. And now I've got my calculated perimeter, and I can calculate my area. And I'm going to say it is the length times the width. All right. Now, I could make lots of rectangles by manually typing them in. You can see how I could just keep making more rows. But what I'm going to do is I'm actually going to use a random function, so I don't have to type it over and over and over again. Let's put in a bunch of cases here, a bunch of rows. I'm going to say maybe like 200. So now I've got 200 spaces for rectangles, and let's change this from manually typed into a calculated thing. So I'm going to edit my formula. I'm going to say random, and the random function, it's the max comma the min. And I don't know if you noticed, but I have a slider back here. We haven't talked about, you can add sliders using this tool up here. And the slider is a way to make a variable that you can use in your functions. If you want to do curve fitting, they might be coefficients, but in this case, I'm going to use it to help me generate rectangles. So I'm going to edit this. I'm going to edit the length and make it random. Max, comma, 0. So it's going to be anywhere from 0 to whatever the max value of my slider is. I'm going to say the same thing for width. X, 0. And notice I've got it now a full table, 200, 201 rectangles, randomly generated. And I'm going to, let's start making some graphs. So first I'm going to explore the length. This is think about what it should be. I've randomly generated 200 lengths. So what do we think the shape of this graph is going to look like? That seems about right? It's about the same number of anything of all the numbers from 0 to 10. I think the width, let's do the width along here. If that's true, think about what you think it's going to look like. All right, did that make sense to you? Does that look like what you think it should? So we have an evenly spaced amount of lengths and widths throughout this data set. So that's interesting. All right. Well, now if I make a graph of perimeter, what do you think the shape is going to be? Take a second to think about it. And I'm going to drag perimeter down here. And this is what I get. I get a distribution in which I have fewer of the small perimeters, fewer of the large perimeters, and mostly somewhere in between. And if we want to start thinking about, well, which are those? I could start looking at highlighting them, and I notice, oh, of course, that's the ones that have the small length and small width. And there's not that many I can fit into this little corner. And if I look in the middle, and I highlight those, which are those? Those are the ones that are spread across the largest space in my graph of rectangles. All right, so now this is going to be the trickiest one for all you math geeks out there. What do you think if I made a graph of perimeter versus area is going to look like? So here's perimeter, the same one we had before. And now I'm going to add area. So this was our original question. What do we think the relationship is between these two? So this is the shape. So then the question is, why is it this shape? What could we do to explore what's going on with the shape? So I might start down here and say, okay, the smallest perimeter is the smallest area. That kind of makes sense. And then maybe up here, all right, largest perimeter is the largest, are these ones up in with the longest length and width. And they're at the tip of this. What's in this corner here where I have like, this one I have a large perimeter, but a very small area. So why might that happen? Well, if I look at that, then what I'm getting is ones that are kind of in the middle, or ones that end up with, if they have zero length, not really in the middle, but along the edges of this, right? I've got, if the zero width, doesn't matter that it's very long, I'm going to have a small area. And if it's a zero length, even if I have a long width, I'm going to have a small area. So that's in here. And then you can get into thinking about, well, I wonder what function might fit this curve here. And again, I'm going, depending on your level that you're teaching, you may or may not want to go this far, but let's say I think this looks to me like a quadratic function. And so I might start by making a couple of sliders, and we'll make one more slider. And I'm going to say we've got A, B, and C for our variables here. And then when I come over here, I can say I want to add a plotted function. And then I can create my function. Quadratic is A times X, which is the perimeter in this case, perimeter squared, plus B times the X, which is the perimeter, plus C. And then I can apply that, and notice here's my plotted function. And now I can, of course, adjust my parameters to try and curve fit that particular function to this set of data. I can adjust the scales of these and to really be focused on this little area here, so it gives me a little bit more fine tuning. And I've got a pretty decent curve fit here. So the sliders can be used for lots of different things. And if I wanted to have rectangles that are not a maximum of 10, but a maximum of 6, I could just adjust this down, and notice everything adjusts and recalculates. So you can think of this as a kind of exploratory way to get into various mathematical features. And if I'm going to jump to this next slide. So what did we investigate? We looked at randomness and variability. We looked at distributions of values. We were studying geometry, making data visualizations. We did some algebra, some mathematical modeling. We added in some statistical measures. So there's a lot of math that we did with this last bit that we were playing with. So I wanted to just throw out a math example for those of you in math land who are wondering, does this apply to me? And I would tell you yes. And there's some great statistical plugins and things that I'll see how much time that I have to demonstrate those. All right. I'm going to demonstrate just a couple of plugins for you. so that you get a sense of some of these ways to extend CODAP and potentially localize for your area for what you want to do. All right, so I'm going to create a, let's see, I'm going to create a new, so I'll just reload this, empty that out. I'm going to create a new document here, and you'll see there's a plugins menu up here. And the first plugin that I'm going to demonstrate is the NOAA weather plugin. So if I click on that, what you'll see here, and I'm going to zoom out just a little bit, is, oh, this is not the one I want to show you. I want to show you the NASA Earth, Air, and Water plugin. NOAA, unfortunately, only covers the US, but NASA has satellites that cover the globe. And so we could put in something like, well, I'm in Bangkok right now. So I'm going to put that in as my location, or I could type in a latitude, longitude. Here's a date range right now. It's set up for the last year. I'll put in metric since we're all using metric here, unlike the crazy US. And right now I can pick what categories of attributes I want about water availability, temperature, sunlight, and click Get Data. Now, when I click Get Data, what's happening is it's actually going directly to the database where all this data is stored. It's downloading it, and then it's pushing it into CODAP. So notice that we just pulled all this data from the NASA database, and it's data about what's happening here in Bangkok. So we have UV index, sunlight angle, sunrise, the day length, the maximum air temperature, precipitation, cloud time. So lots of really cool, interesting data. And notice, see the structure? We're using the structured table of CODAP. So that's the city or the location, and then all the measurements. So I could compare to like maybe where I come from, Boston, and I'll get the same data. So now I have data about Bangkok and data about Boston. It might be interesting to start exploring some of that data. Maybe if I make a graph, I'm curious about graph of maybe date versus max temperature. So that's very interesting. Notice that I have, this looks like there's two different patterns. Now, how can I further understand what I'm looking at? Because this is all the data from both cities. Well, one way would be to drop the location into the middle, which would then color by location. But I can also drop this categorical variable either on the right side or in the top. And if I drag it, if I drop it on the right, I now get two fully separate graphs. And in fact, you'll find that you can make, let's see, you can make multi-dimensional graphs here. Now, of course, at some point you get to where it's hard to understand. But, if I wanted to then further break this up by month, I could do that. Now I have a graph for every month for every location of max air temperature. And this is hard to see because we've got too many of these graphs. But you can see what we can do here is that you can add multiple variables, multiple dimensions onto one graph. And this was a very nice plugin that lets me pull data from any spot on Earth. The sampler, let's see, let's look at the sampler. I'm going to reload this because I haven't saved it, and go to plugins, and under simulation, you'll see one option is sampler. And the sampler, I actually could do, remember how we talked about like if I want to do coin flips, or I wanted to even generate random rectangles. I could come down here and I could say that I wanted to set this to be the numbers 1 through 10. And so now I have a bunch of balls here, 1 through 10, and I could name this length, and then I could add another device, and we'll do another 1 through 10, and I'll name this one width. And now I can decide up here how many samples do I want to collect, and how many items in each sample. So maybe I just want to do one sample of 200 items, and that's going to give me the same. It's like a set that I generated with the random functions. Now it's set up so there's length 9 with 10. It's going to push that out into our data here. Now I'm going to speed this up so that we don't have to wait, and you can see that it just generated all those rectangles for me. So there are lots of interesting statistical models that one could explore here. One example I can talk about in a middle school classroom, we had students that went out and they actually went to find crabs along the ocean, and they sampled them, and then they checked whether they were male or female crabs, and they found 70% were male and 30% female. And so they were wondering, is that like just by chance? Is that a fluke, or is that something real? So the way the teacher worked with them is they generated a model here of, well, what if it's 50-50? What if it's 50-50 male, female? And you generate lots of samples of like going to the ocean and sampling. And then you can see, where does 70-30 show up in that distribution? Is it somewhere likely, or is it not likely? So it's a way of getting at statistics measures that you might think, I have to wait until I'm in college before I start to engage in these concepts, but this worked in a middle school classroom. All right, there's a whole bunch of other plugins. Story Builder you saw when I did the random rectangles. Basically, it allows you to set up a document and in multiple ways and sort of walk through that. So you could set something up in advance for students, or you could have students build their own story as they tell you a story about the data that they were exploring. There's a whole set of learning modules that is called the Story Cube project, which is about how do AI models work? How do machine learning models work? And it actually embeds a plugin in CODAP that allows you to train a machine learning model right in CODAP and explore what's going on with that. So that's another set of learning materials that are available, and it uses a plugin in CODAP to do this machine learning. I'm currently working on, but it's a prototype, so I can't really put it out there yet, of a tool that allows blind and low vision students to engage in data exploration. What it is it connects, Devi is a plugin that connects a large language model to CODAP, so that I can actually just talk to it and say, create a graph of something, describe that graph for me, sonify the graph for me, so I can get a soundscape of that graph. And we're hoping that this will work to help students who are normally left out of this kind of inquiry to be able to engage like their peers. And in fact, we're finding everyone likes this plugin. Everyone wants to use it. So we're exploring the possibility for that. All right. I mentioned I was going to show you how do you set up the documents like I was demonstrating. So when we have a document that we're looking at, let's see, let's pick something we've got. So let's say I wanted to save this. I go up to File, I choose Save, and now I have two options. I can either save it to Google Drive, and if I do that, while I continue to work with it, it will auto-save all my changes. Or if you don't have access to Google Drive, you can save it to your local device. So clicking Load, and it will just download the current state. It won't be able to keep updating because it would then download every time you made a move. in CODAP, but you can have it download whenever you reach a certain time that you want to save that state. But the way that you're probably going to use this with students, of course, you're going to save things, but there's an option here where you see where it says share and get linked to shared view. So if I click that and I say enable sharing, it says, please wait while we generate a share link. Now, what it did is it made a copy of my document, a snapshot, put it on a server, and now this link, which I have, I can give to anyone, and everyone gets a copy, their own copy of the document, and then they can explore it themselves. They might then make their own kinds of changes and share it on with somebody else or back with me, or you can share with the whole class if you have people share to a shared Google Doc, for example, or some kind of mechanism in your learning management systems that you might be using where you can assign things and retrieve things back from students. So this share link is it's a very flexible way to be able to do that. There's also an option to just embed CODAP as it is into a web page. So if you wanted to build stuff around CODAP, you could build your own web page and embed CODAP right into the web page itself. And in this case, it would embed this document or this setup. So a lot of options for working with CODAP. And as I mentioned, the share link you give isn't the original. It's not a collaborative environment in which multiple people can work on it at the same time, like a Google Doc. You have your version that's yours alone, and you can share a copy with other folks. All right, there's a bunch of helpful resources on this slide here. Again, you have the link to all these slides, so you can get all these links yourself. The CODAP website, we have some FAQs on how to assign CODAP documents and collect student work. I know I went through that quickly. We have some other example data sets, but I would encourage you to try and find some stuff that you could localize. We have help pages and a forum where you can ask for help from other CODAP users. Tim Erickson has been a friend of CODAP and from even before CODAP, and he wrote an online book that is freely available called The Wash in Data, and it's about introducing students to data science through CODAP. And so I highly recommend that. And if you want to contact the project, which will come to me and some others, you can contact CODAP, or if you just want to send me something specifically, you can send to ddanlin@concord.org. The next tool that we're going to talk about is SageModeler. And I mentioned earlier about how I initially started by developing simulations for students so that they could explore the atomic world or various other kinds of simulations that I started creating as well that were more macro level. But these were all simulations that I created or my team created for students to explore some phenomena. And one of the things that one of the goals was to have students engage in modeling in ways where they're creating the simulations. Now, I've been working for a long time with Joe Kraychek from Michigan State University, and he had a graduate student who had the original idea of a program called Model It, and this is Sherry Metcalf. And SageModeler is a tool that's inspired by Sherry's original work. And I remember Joe coming to me and saying, we've done a lot of great work with modeling, but let's get students modeling. And so this was SageModeler development is a collaboration between the Concord Consortium and the Create for STEM Institute at Michigan State University. And the whole work is originally inspired by Sherry Metcalf's graduate work many years ago. All right, what is SageModeler? So SageModeler is also free and open source and browser-based, just like CODAP is. In fact, SageModeler is built on top of CODAP. Pretty much everything you can do with CODAP, you can do with SageModeler. but the focus of SageModeler is systems model. I mentioned the collaboration with MSU and Sherry. It has a little bit less of an audience right now, about 130,000 active users per year in 15 languages, 30 countries. It too, like CODAP, I think that it has a low bar for entry for students and has a high ceiling. And part of that is because we can do 3 types of modeling, and I'll demonstrate each of those 3 for various levels of modeling sophistication. And the goal here is, if you ask students how they think something works, they almost always have some idea or at least some speculation about how they think something works. And for the most part, the way that we've gotten students to express that is through drawing a model of something. And that works well for putting something out there for discussion, but they can't really test their model, right? If it's a drawing, you can't simulate the drawing. And so what we wanted to do was create a tool where I could take my mental conception of how I think something works, place it on a canvas. The way that we design that expression provides an opportunity for peer review, for discussion, and then I can also simulate it. And in addition to that, I can pull in data to SageModeler just like we can pull in data to CODAP, and then compare the output of my model to the output of the real world, which then gives me additional feedback on my conception of the system. And because you are doing computational modeling and you're doing computational modeling of systems, building a SageModeler model engages students in modeling, systems thinking, and computational thinking all in one exercise. And so we'll take a look at how that's done, and you'll be able to see for yourself how we do that. All right. I want to start by talking about a story. This is a true story. In the 1950s, there was a malaria outbreak in Borneo. And the World Health Organization jumped in to help with this and sprayed DDT everywhere. That's at the time when we didn't realize DDT was not so great. It worked really well, knocked down all the mosquitoes. The malaria went, down quite well. But not too long after that, people's thatched roofs started caving in. And then not too long after that, all the cats died. And then there was an explosion of the rat population and plague and other diseases associated with rats. So what happened here? This is the idea of, oftentimes when we think of a problem we want to solve, we focus on this one little thing. We don't see how it is connected in the broader system. What ended up happening was the DDT knocked down the mosquitoes, but it also killed a parasite that affects caterpillars that eat thatch. So the DDT killed the prey of the caterpillars started eating everybody's roofs, the roofs started caving in. Now there's a lot of dead insects on the ground full of DDT. The geckos are eating them, and the geckos are becoming poisonous with DDT, and the cats are eating the geckos, and then the cats died. The cats died, well, nothing was keeping the rat population in check, and so that caused this whole problem. They literally ended up parachuting cats in to solve the problem. But if people were thinking more systemically from the start, maybe it wouldn't have had this, maybe the problem could have been solved without all the side effects. And I'll show you, I made a SageModeler model of this particular thing so you can see what that looks like. All right, so what you can see here, let me zoom in a little bit, is we have these boxes. Each box represents a component of the system or some variable that might be changing in the system. You can also see that we have these arrows that are pointing from one variable or one component of the system to the other. And notice that the arrows have a direction and a shape and a color. So this tells us actually a lot about how the person who made this model thinks of that relationship. So for example, I'm going to hide this graph for the moment. For example, if I double click on this arrow, you can see that it says an increase in the amount of DDT causes live mosquitoes to decrease by less and less. So what this is saying is, as soon as you have some DDT, it kills a lot of the mosquitoes, and you get diminishing returns over time. You can spray more and more, but it's just doesn't have as much of an effect. And notice I set up this relationship just by looking at the words and the graphical depiction of that. And so, and notice every time I change something over here, it's changing over here. And so that's why the color and the shape tells me about the relationship. And so if you look at this, we have the amount of DDT is going to have and I can also turn on, if I want, I can turn on the relationship symbols, which will show positive and negative. So DDT has a negative effect on the mosquitoes, which had a negative effect on the number of people with malaria. I mean, a positive effect on the health of the people who had malaria. So that should actually be renamed. This variable should be better renamed, or I'd have to change this relation. And again, the DDT affected the wasps, which affected the caterpillars, which affected the roots. And then having DDT also meant you had dead wasps and mosquitoes, which then affected the geckos, which affected the cats, which affected the rats, which then caused there to be people with plague and typhus. And notice I can simulate this by pushing the simulate button up here. And as I adjust the amount of DDT, we see that all through the system. So this one variable back here causes all this downstream change in the system. And notice that what it's saying is if I have a lot of DDT, then I have very few live mosquitoes, but I might end up with a lot of people with plague. And the opposite is true if I have less DDT. So we don't think of this as over time as much as if I had different amounts of DDT, what would that do in the system? And if I simulate this system, which I'm simulating it live here, but I can also record that data here. And so, for example, I'm going to, I'll show how that's done. I can click record continuously so that it's going to record all of the values of the variables live while I slide this. And you can see that it's recording it into the table. Notice that looks like a CODAP table because it is. I'm going to hide that table. And then I'm going to, here, let's start by making a graph of the amount of DDT. Actually, make a graph of the amount of DDT. And then I could add things onto that. So I might have the people with, that's over time. What I want to look at, what I want to look at is, I'm going to make a graph here. Notice it looks like a CODAP graph. And I can drag, instead of dragging from the table, I can drag my variable names right from here. So I might say, amount of DDT versus people with malaria. And then I see there's a relationship and that makes sense because that's related to this relationship that I set here. So there's lots of ways to explore that. Now, I don't have actual data that I can compare for this particular phenomenon, but we'll look at some other examples. All right, so with SageModeler, A couple of important links. There's the website that's about SageModeler and has lots of resources there. And if you want to launch SageModeler itself, then you could click on this sagemodeler.concord.org /app link. Now, I mentioned that there's various kinds of modeling that SageModeler can do, and we're going to talk about when it's appropriate to do some of these different kinds. There's model diagramming, so that's simple diagramming. You might want to do that with elementary students. There's static equilibrium modeling, which is what we just looked at. That example with the mosquitoes in Borneo was an example of that. And then there's a dynamic time-based modeling, which is basically systems dynamics modeling. It's a much more complex kind of model to set up and use. So we won't be able to do too much of that today, but this is a kind of modeling that if you want to model a system over time and how it changes over time, that's the kind of modeling you use. If you're wondering about these different kinds of modeling, there's some links here to an article about that and a deeper dive into the difference between static and dynamic modeling and when you might want to take each of those approaches. So again, it's the same link to the slides from before. It's one big slide deck. So if you have that link, you have access to all of these things. All right, so let's look at some of these different types of modeling that we can do with SageModeler. So this nitrogen cycle model, this was actually done by, I believe it was a early middle school student. And this kind of diagramming mode, it's good for things like food webs or mind mapping. There isn't any simulation involved. And you can optionally define those relationship arrows. You can say which way there's a cause and effect relationship, but you don't have to say whether it's positive or negative, or you could. It's up to you. Let's take a look at this student model. And so notice here, they put in their variables that are part of the system. They have arrows. The arrows are all gray, so they haven't defined any, like this increases or decreases that. They're just saying, here's a connection between the two, and they added words to describe that connection. In order to add words to an arrow, here's one without one. I could click on the arrow once to highlight it, and then I click on it again, and it will bring up a box for me to type something. Right, so this, you can imagine, this is a lot like some other tools you might have used, mind mapping tools or food web kinds of tools. Very simple. If I wanted to do a relationship, I could, double click on an arrow or on one of the variables. In this case, I clicked on a variable, so it says an increase in ocean atmosphere. That causes atmosphere to, you would say, increase or decrease. But you might, when you're doing this kind of a model, these don't necessarily have to be measurable variables. They might be concepts, things like that. What you'll see is if you want to have a model that you can simulate, though, you really do need to have every variable there is something that should be able to be calculated on some kind of scale or measured on some kind of scale. All right, let's go back and let's look at another example. So we all remember the past epidemic. So here's a model of a generic epidemic, not necessarily COVID. And we're going to use static equilibrium modeling for that. And what it shows is a state of the system given the inputs. Okay, you can almost think of it like a visual spreadsheet with a bunch of linked cells. So let me open up this version of the model. Okay, so we have our, this is one, again, because it's not behavior over time, it's sort of like the overall impact of the of this epidemic, the number of infected people maybe. And you can see we have a whole bunch of variables: effectiveness of vaccine, number of vaccinations. Both of those affect the effectiveness of the vaccination program. There's how infectious the disease is, how many susceptible people there are in the population, how many people are being you're bumping into each day, and all of this I can turn on the simulation, and you can see that as I adjust certain things, that affects all the things that are downstream from that. And we can have multiple things all pointing into one and affecting that. If I double click on that, you'll see that I have options to set all these different relationships there. And we have a couple different ways to combine them. One is to average the impact of everything, and the other is called limiting factor. Whenever one thing would cancel out the rest of the things, that's when we would use limiting factor. So for example, if the disease was not infectious at all, well, then you're not going to get any infections. Doesn't matter how wonderful or how poor your vaccination program is. Doesn't matter how many people you bump into. If it's not very effective, you're not going to have. So that's why limiting factor was used there instead of average, because otherwise, if it's average, you'd always have some infections, even if you never came in contact with somebody or there were no susceptible people or something like that. All right, so that's static equilibrium modeling. Notice I have my inputs. So these things that don't have anything pointing to them are what we would call our independent variables. And everything that has an arrow pointing to it, its value is set by the things that are pointing to them. So those are dependent on the value of these other ones, so they don't get their own slider. That's why some things have sliders, some things don't. But, looking at this, I just want to say, before I even start simulation, if I were running a class and the students created some kind of model, there's tons to discuss right here. Which things did they choose to put into the system? Which variables do they want to represent? What relationships have they put in? Do they make sense? Are there different ways that people are thinking about this system? So there's a ton to talk about even without doing the simulation. And then once you do the simulation, a student can sort of check their own thinking about, well, if this goes up, then I expect this other thing to go down. If it doesn't, they can go back and make changes to their model. All right, let's look at the same phenomenon, but through a dynamic time-based mode. All right, I'm going to open this model. Now notice it looks pretty similar to our last one, but we have a few new kinds of things in here. With dynamic modeling and systems dynamics modeling in general, you tend to have a thing that's an accumulator, a holder of stuff, and flows. So they're called stock and flow traditionally. The language we use with students, we call them collectors and flows, because stock is not a great student-friendly word. So we have collectors and flows, and then we have just regular variables like we did with the other ones. And notice when I turn on the simulation here, instead of bar graphs, we get line graphs. And this simulation is basically calculating 30 times. Each new step calculates and tracks what the current set of values of all the variables are to calculate the next step. And so in this particular situation, we have susceptible people who become infected people. And this here is the flow rate. This is the daily infection rate, right? Do you remember when we, there was a lot of talk about flattening the curve of how many people were being infected each day? Well, let's look. If we reduce the number of people contacted, that curve flattens out. If we increase the number of people contacted, then it goes up. And so now when we play with variables, we're playing with the starting values, and then we see how that bubbles through the system and then the behavior of the system over time. Here's an example where I do have some data. So I'm going to go back here, and I have put this is COVID data from Jakarta, the very first wave of COVID data in Jakarta. So I'm going to click download first wave. You'll see that it got downloaded by my browser. So I'm going to go back into my model here. And just like I did with CODAP, I'm going to go into the downloads, grab that data, and drop it into SageModeler. Now notice I have some data in here that I can compare to my model. So in order for me to have model output, I have to record the model. So I'm going to do that. I'm going to push record. Then it's going to record all 30 steps of the model. I'm going to close my data table there. And so, for example, if I wanted to make a graph of the number of new infections per day, I'm going to click here, create graph, and there I have a big version of that. But I might want to add on to that infected individuals. So I'm going to add that. Now I could add it on the same axis, the same y-axis if I added it here. But I know they're very different scales. So I'm going to add it on an opposite y-axis. So now I have two different things on the same graph. Now this is my model output. Maybe I'll even rename this model output so I don't get confused. So you might say, well, how does that compare with the real world? So I'm going to create a graph. And just like in CODAP, I can drag the attribute names from here. Let's make the same thing. I'm going to, in this case, instead of steps, it's the date, right? Because each new day, there's a new state of the model. And I have, this is number of new infections. So that's daily cases, daily positive cases. Interesting. That looks like a similar pattern. Or maybe I have my total cases. I'm going to put that over here. So take a look at this. This is the real world. Now, the real world data is always going to be messier than the perfect smooth data from a model. But if we look at the trends we have here, our model is doing quite a good job of modeling what happened in the real world. Now, remember, we were able to set this all up without doing any formal programming, without writing equations, just creating our variables and setting the relationships using those drop-down menus with words and pictures of graphs. So this really starts to get, you can get some pretty complex modeling done with the dynamic modeling and still not require programming or equation writing. And because of that, whether you're doing this time-based dynamic modeling or the static equilibrium modeling, you can create simulations and make that possible for a much wider range of students, right? They don't require to have, mastered a particular programming language or have in-depth knowledge of mathematical equations in order to still conceptually engage in modeling, building their own simulations, and comparing with data. So for me, this was really a kind of eye-opening tool for teachers to be able to, I can't think of any other way that students could engage in this kind of modeling this easily, at least for getting started. There are tools where students can engage in building their own simulations, but there's typically quite a steep learning curve before you get to do something interesting. All right, so let's build a simple flooding model together, okay? I'm going to launch SageModeler. So I have a bookmark for that. Oops, I went over my slideshow there. Back to, sorry. All right, so we launched SageModeler. And our goal, let's come back to this for a minute. Our goal is to think about flooding. I know that flooding has been a very serious problem here recently in this area. And so if you wanted to start modeling what's going on with that, what are some of the factors that might be affecting flooding? Well, let's think about what we would want our variables to be. So I know that the flooding in this case was mostly due to torrential rain, but it's also going to be impacted by sea level rise, so we might also include that. But let's think about some variables. So let's say that I'm going to put something on here, maybe amount of rain, right? So I dragged new image onto my canvas, and I'm going to search for an image for rain. Now, you don't have to put images. It's up to you, but I will tell you that students really enjoy customizing these models for themselves. And notice what I'm going to put in here, amount of rain. And I specifically did that because that is clearly a measurable value. Oftentimes when people first start doing this kind of modeling, I might say, okay, well, let's model climate change. And so what's a variable you want to put in your model? And so they say the Earth. I say, great, the Earth. Is the Earth going up or going down? And they go, no, like the temperature of the Earth. Oh, the temperature of the Earth. Right, a measurable variable. Now, it doesn't have to even be a hard variable. It could be like happiness. It could be anything that can be on a low to high scale or a quantitative value. All of those are good for SageModeler models. You don't need to have all just hard quantitative numbers, but it does have to be calculable because, and you'll see with those relationships, right? The relationship says as one goes up, the other does what? So if I were to say as the Earth goes up, I point to something else, that doesn't really make sense. I have to have a measurable variable. All right, so we have amount of rain. What else might impact the flooding level? Let's think of something else. Well, it could be the strength of the storm, right? So I'm going to pull down something and I'll look for maybe storm. And let's see. Maybe we'll do this. Strength of storm. But then I might think, okay, well, and I can even start by doing some relationship. The strength of the storm is going to impact the amount of rain. So notice I grabbed this and I dragged it over here until that lit up, and then I'm letting go. And it's a dotted line now because the relationship is not set. And I can set this by double clicking here, here, or here, on either variable or on the arrow. So I usually pick the variables to double click on because they're bigger targets, easier to find. All right, so it says an increase in the strength of storm causes the amount of rain to, I'll probably say increase. That makes the most sense to me. And then I have a choice of about the same, which means if I double the strength of the storm, I'll double the amount of rain, or I might say a lot, so it like has a big increase and then sort of levels off, or a little, or more and more, or less and less. And notice we get the different shapes over here. You could also, if I said decrease, then it would give me a different relationship. There's one other option called vary, which allows you to actually draw your own relationship. So for example, if you were, oftentimes pH is used in a biological system. And very low pH is not so good for biological systems. There's some like middle ground that's pretty good. And then very high pH is also not so good. So you might want to draw that to be your relationship. So you can make custom relationships, or maybe you want to have there's like a tipping point. So I'm going to draw like if nothing happens and then suddenly something happens. So you could draw relationships like that. For this, we're just going to keep very straightforward increases, and I'll say about the same in this case. But then I might back up and go, well, what's impacting the strength of the storm? Well, then I think it has to do with, I know that it has to do with sea temperatures. So I might drag this in and I'll look up for ocean. And let's see, sure, I'll pick that. Call it ocean temperature. Another thing to notice here, notice I'm not saying increase in ocean temperature. I don't want to build into my variable name the direction I think it's going to go, because this is a model. It can go anywhere. It could go up, it could go down. Otherwise, for example, if this said increase in ocean temperature, when I go to do the relationship, it will say an increase in ocean temperature, which gets very confusing. So you just want to specify the variable, you don't want to specify the direction. And so I'm going to put that relationship over there. And then I'm going to move these all over. And maybe I'm going to add in the air temp. So maybe I'll put in something to represent air. I'm not sure there's a good one for that. Here, we'll just gas. So we'll say air temperature. I can actually, you know what I could do is I could use a thermometer. Use that. And then air temperature is going to be affected by carbon dioxide. Here, I'll use soda to represent that one. We got our fizzy soda, carbon dioxide. And ultimately, we're going to have things that we can start getting into. What are the emissions from factories and cars and that kind of thing. Now, this is a pretty linear model, which is okay for now. And I'm going to set some relationships. So an increase in carbon dioxide because air temperature increase. Maybe I'll say a little or something like that. And then notice once I have this open, I can just start clicking on different things, and that will stay open. Increase in air temperature causes ocean temperature increase. Be about the same. And then increase in ocean temperature causes strength of storm to increase. I don't know. It seems like it's like this, but I'm not sure. So now I have something that I can start talking about and something I can build off of. This is kind of like a backbone of the model. And I could simulate that. And so as one thing changes, these are all also changing. I could record some data about that. So it's going to record all of the changes in the variables. And stop recording. And I have some related data as well. Let's see. I was looking at sea level rise, so we'll have to look at my my real world data and see what we get. All right, you come over, I downloaded that. Let's pull in what I had. Hopefully there's some stuff that relates to this model still. All right, well, we have year and we have temperature and we have CO2. So there's some stuff in here we could look at. So let's say that I wanted to look at the connection between CO2 and temperature, for example. I could create a graph. And from my model, I could look at carbon dioxide and air temperature. Oops, I missed dropping it. And so we get something like that. And from my real world data, I could also do that. We get something similar. So at least it looks, at least from choosing one of the linear relationships, that seems to make sense given our real world data. And we could go on to expand this. If I were ways that I would challenge people to think about expanding this would be, well, in the same way that the 3-year-old always asks, but why? But why? You might say, well, what's affecting this thing? Or what are there other things that are affecting air temperature? Could be possibly cloud cover or some other types of things. Carbon dioxide in the atmosphere will have lots of impacts, but it can also, if you want to expand this further, carbon dioxide in the air is going to cause ocean acidification to happen. So you could start building out in that direction. amount of rain. We don't have any impacts of the rain. Like, what are some of the impacts of this thing that you span out to have multiple impacts? And then maybe, because you don't want your students freaking out about the world is coming to an end, what are some policies that we could put in place that could impact the system to mitigate some of the issues that we have? Right? So you can imagine building lots of branches out off of this backbone in different directions, and depending on how deep you want to go in various levels. And you saw as we built this together, it's pretty straightforward. I like to use the images, so I usually drag new image down to make a new variable. I could just use generic blue boxes, then I don't have to worry about images. Oftentimes when I'm doing it myself, I'll just use the blue boxes because I want to quickly build something up. And but students really like, you might have the occasional student you have to say, okay, pick something and move on. Some students will spend forever trying to pick a particular image, but or finding something. but I would encourage you to let them do that for at least a little bit. All right, let's come back to our slideshow here. All right, I want to talk a little bit about, I mentioned earlier that this kind of modeling links together systems thinking and computational thinking. And this is a framework image that I worked on with the group at Create for STEM. And we started with what we knew about just any kind of model. First, you have to think about the problem you're going to solve. And then there's a sort of constructing, revising part. So you define, as part of that, you are thinking about what you want to include as variables. Now, right there, you're already starting on a major systems thinking practice of defining the system. What are the boundaries of the system? What counts as a component? Okay, now that is important because, again, like the 3-year-old asking why, you could end up going all the way back to the Big Bang as part of your, the beginning of the universe as part of your model. And you don't want to do that. You want your model to have a pretty good representation of the system, but you don't want to include every tiny thing because then it will get too complicated. So you've got to think about what variables you're going to include. Now, remember how I said the variables have to be numeric or some kind of calculable value? Well, that come over here to computational thinking, decomposing a problem such that it's computationally solvable. So when I think about the system, I'm not just thinking about what's the boundary, but I'm thinking about what are the calculable variables that I can use to break this down into something that I can model computationally, right? So already I'm pulling in two practices from systems thinking, computational thinking. And then we have design and construct the model structure. That's where we're drawing arrows from variables to other variables or other components. Well, we're certainly engaging in causal reasoning, right? We're saying this thing has an impact on that thing. And you'd be surprised. It seems simple, but you would be surprised at the challenge there is for students in making sure they have the direction of the causality going in the appropriate way. Recognizing interconnections and identifying feedback. So in systems modeling, you've got your interconnections, but there's also feedback in the system, which causes a lot of the behavior that we see. And then framing this as behavior over time for our dynamic modeling, we have that kind of thing. And then predicting system behavior based on system structure. And one of the things that we didn't get into, but you'll see that certain patterns of how variables are connected to each other cause the system to behave in a certain way. And so there are actually subgroups of variables and relationships that are common across many systems, and you'll learn to identify those. Coming over here to computational thinking, creating artifacts using algorithmic thinking. So every time you've linked together a bunch of variables and specified how that relationship is, that's algorithmic thinking, right? This affects this, and in which way does it affect? It's going up, this one's going down. It's a basic kind of algorithmic thinking, but it is. Generating, organizing, and interpreting data under computational thinking. And we certainly we saw that when we simulate it, we can then record the state of the model in various states. We did a bunch of testing and debugging. So I might say, oh, I don't think that relationship works with this real world data. I should change the relationship, or maybe I'm missing a variable, or I have something extra in there. And then making iterative refinements. And this is the kind of thing that we do all the time. I'll talk about that a bit when I design lessons around this kind of work. I always do it in an iterative way rather than it being the culmination of a long unit. We start building as we go, and we refine our model as we learn more. And you'll see that also here in the modeling process. So we have a construct and revision. We have a construct and revision cycle, and then we test and debug the model. Sometimes the model output doesn't match how we think it should behave, or sometimes we get pulling some outside data and it doesn't match that. So we go back to our construct revise phase. And sometimes it's, we're just in the next lesson of the unit and we've got some new information and evidence so that we want to add that into our model. So we do another iteration. Ultimately, we hope to create a model that helps to explain or predict the behavior of a phenomenon or a design solution to a problem. So we pulled together systems thinking, computational thinking, modeling. It's a very rich experience for students to engage in this kind of thing in the classroom. Our thinking behind this framework here is elaborated upon in this paper. So there's a link at the bottom of this slide to the full paper in which we published this particular framework. All right. Saving and sharing SageModeler models. It's exactly the same as CODAP. You'll notice if we go back to any of our SageModeler models here, this bar at the top looks almost exactly the same as CODAP, or at least the current version of CODAP. And you click on this and we get all our same menu items. I can save to Google Drive or a local file. I can come down and I can share it and make a link to a shared view. So I can enable the sharing. I can embed it in a web page. All the things that we could do with CODAP, we could do the same thing with SageModeler. So you could either set up a blank thing if you don't want students spending a lot of time picking variable images. You can populate this and just have a blank canvas, but the palette is populated with things for them to drag onto the palette. Because I can drag any of these things on to make a new variable. So same way, CODAP and SageModeler, easy to save and share, and use those in assigning models to students. You might assign them a partially built model and ask them to build it out. Maybe you want to assign a model that isn't correct and have them try and debug and figure out where it's not working properly. So there's lots of ways to think about using SageModeler, engaging in computational thinking and systems modeling. And again, I also like to think of this as maybe an early visual programming language for very young students as well to begin engaging in some computational thinking. I know that SageModeler has been integrated with several units, and that water quality is an important phenomenon in this region. So there's some links here to curricular units that have SageModeler built into them. This is all part of Concord's learn.concord.org website. I'll go to that place now. The main, if you just go to learn.concord.org, you'll find this says our STEM resource finder, and there's hundreds of things here that you might find useful besides what I'm talking about today. And in the collections, most projects that we have at Concord create a collection of curricular materials. And so if we go down here, sorry for the extra scrolling, Passed right by it. System modeling with SageModeler. So this is our collection of curricular resources here. You'll see there's some intro to modeling options for lessons, and then under investigations, there is several here, and this how healthy is our stream is a water quality one. If you log in, oops, I need to do that. If you log into the STEM Resource Finder, it's, again, free to use. Making accounts is free. If you register and then log in as a teacher, you will get additional things will show up here, like teacher guides, and other links will show up that only the teachers see. If you want to just peruse the water quality investigation and teacher guide here, you can do that without logging in, because I'm giving you direct links to do that. But I do recommend you log in. You can set up classes, you can assign materials to students and automatically collect all of their work into a nice dashboard, so you can see all the answers students are giving in their models that they're making. Some helpful resources for SageModeler. Of course, there's the website. It has help pages. We have pedagogical supports for curricular units. I mentioned that I would talk about our approach in that relation to iterative modeling. So I am going to show this link briefly. And so this is a document that describes our design process. And I just want to focus in on this particular diagram here. Generally, when I think about designing some lessons or curricular units around SageModeler, it starts with an introduction to the phenomenon, getting students sort of interested and excited, connecting it to the real world for them, and ideally something that they care about. We often use the driving question board, where we ask students, well, what questions do you have about this phenomenon? What questions would we need to answer in order to understand the phenomenon? And I actually still start with a paper pencil model, a drawing. It's a little bit easier for students to engage in. And then we try to transfer our idea of the paper and pencil model to a SageModeler model. And there's actually a great opportunity there to talk to them about the different kinds of modeling. What does it mean to build a computational model? What kinds of computational thinking and systems thinking are you engaging in order to go from just an illustration that you've drawn to creating this simulatable kind of model? So it's a great opportunity for that conversation to make explicit some of these practices that they are learning. We then usually investigate some part of the phenomenon. We do a reading, a demo, watch a video. There might be a hands-on experiment, a lab that they do. And from that, they revise their initial model, because they're just sort of speculating about how they think something works. Now they have some information. So they might add something, they might trim something, they might change some relationships. We then have them peer review, like they look at each other's models and get a chance to revise. The teacher then looks at all of the models and picks a couple of examples to talk about. And they might talk about issues with the disciplinary core idea related to the thing, or they might talk about general modeling issues. And then we come back and we revisit the driving question board. What did we already figure out? What new questions do we have? We investigate again. We revise our model. We do this as a cycle until it makes sense for the end of the unit. This is typically how we design units, and we found that this is a really engaging way to have students, and not too overwhelming. They have to sort of build it all at once. I have seen folks who they go through the whole unit, they say, okay, as a sort of culminating activity, I'd like you to build a SageModeler model of your understanding. At some level, they're using it more like an assessment in that case, as opposed to a tool for exploring their understanding of the phenomenon as they're learning it. but that's also a genuine use of the tool as well. So however you find it useful, that's the right way to use it. As long as you're getting students to engage and do some of their own thinking and you're not doing all of the modeling for them. But in this webinar, like the flooding one, I kind of walked you through it. But I don't recommend you do that with your students. You want them to say, if we were in a more intimate situation, I might say, well, what new variable should I put out here? Or I'd throw it back to you to start building it, and then we would come back together and share. Because we could create share links of all our models and then share them with each other. All right. In terms of contact, um, again, you can contact the whole project by emailing SageModeler@concord.org. That will come to me and several others. Or again, you have my personal email, ddamlon@concord.org, if you want to get in touch with me. You know, as mentioned earlier, we scratched the surface of those two tools. But in addition to those tools, the Concord Consortium has been around for 30 years. We've been developing materials during that time. Much of our materials are still available that we developed over our history of our organization. And I've just wanted to put in a few links here at the end if people want to do additional exploration on Concord's websites and for various tools. The learn.concord.org, I showed that briefly. There's the SageModeler collection of stuff there, but there's collections of all kinds of other things. There's a fantastic set of earth science related simulations and resources. Nothing out there like this to help students really engage with building their own, tectonic plates and seeing what happens as they move and interact, and cross sections, and there's a volcano and an earthquake explorer and just wildfire explorer, all kinds of very cool simulations in the earth science collections. As I mentioned, there's an AI in education collection, and uses a plugin inside CODAP to allow people to train a machine learning model themselves, which is really cool. You build your own AI system. The interactions curriculum is one that, again, it was a collaboration with Create for STEM Institute at Michigan State University, Joe Kraychek's group there. This is a full year curriculum, interdisciplinary, but based on atomic level interaction. So how does the atomic world and the interactions going on down there create everything that we see around us and everything that we experience? And related to that, these molecular workbench simulations. There's also another tool for folks who are interested in doing some mathematical modeling called M2 Studio. I haven't gone into that. I don't really have time to show much about that, but you may want to poke around in there. And we have a whole separate assessment portal, which is based on the next generation science standards from the US. And there are, I don't know, something like 100 different formative assessments. They take 5 to 10 minutes for a student to do, and they're across elementary and middle school. You're welcome to explore around there. It's all freely available. And I wanted to thank everybody for coming today. I know that this was a long time to take out of your very busy schedules. I really do hope that you found something that will be useful and impact your classroom. That's our goal at Concord, and my goal personally. And I hope that we're able to continue and do more events like that.